So, good evening, everyone. Am I audible? Okay, yeah. So, I will be the TA, teaching assistant, or for this particular live interaction session. So, I welcome you all for this live interaction session for the course Waste to Energy Conversion. So, let's just wait for a few minutes for others to join before we begin our session for today. So I think we can start our session. Let me just share my screen. Oh, sorry. I hope my presentation is visible. Let me introduce once again. Good evening, everyone. Welcome to the week 1 live interaction session for the course Waste to Energy Conversion. This course is offered by Professor Prasanajit Mondal from the Department of Chemical Engineering, IIT Roorkee, under the NPTEL program. Myself, Pratyumnan, a PhD research scholar from the Department of Chemical Engineering, IIT Guwahati, Assam, is one of the course team members who will be responsible for conducting the live interaction session every week. Before we move on towards the week 1 session on introduction and characteristics of waste material, let me ask a important question on why is there is an importance of converting the waste to energy, or why is this topic of converting waste to energy is gaining so much popularity and relevance in the recent days, or how much understanding or uh, idea you guys have on why it is important to study about the topic of waste to energy. So one person, yeah, it is fine that it is to make something sustainable, but how you are going to make that sustainable? Can you just repeat what you said once again? Yeah, that is one. So by doing that, we can actually make sure that there is a systematic way to be like the exact term what is introduced in what is said in the course is the systematic solid waste management, so that we are able to reduce the load that is there in the landfill, so that the wastage gets reduced. And apart from that, we can, okay, just a second. Yeah, so there is one response in the chat box which says that since there is a lot of waste getting generated and there is a depletion of the coal sources, so we are looking for energy from the other sources, and that is one of the reason why we are specifically interested in taking out this waste as a material to convert to energy. Yes, exactly. So these two things, one thing is to make sure that there is a sustainable waste disposal system so that the waste that keeps getting generated does not get accumulated upon the surface. And then the second thing is that the to meet the energy demands, because at the end of the day the population is increasing rapidly day by day, so we need to satisfy or meet the demands of the humankind. So in order to do that, we are actually exploring a lot of other energy alternatives. So among one is the waste, uh, the energy extraction from this waste material. Of course, there are also other renewable energy resources like solar, wind, and hydropower, etc. Among them, the waste, or you can also make it something specific like this biomass. All this stuff is also used up to satisfy the demands that is used up to satisfy the demands that is there at present. So let me just go back to the slides. So before moving on to this slide, so let's just discuss a bit about what are the types of waste, how, what are the sources or the origins of these particular waste, and why we are interested in them. So if you see the waste material, so the exact definition of waste is nothing but it is just like byproduct. So in any process, whatever that byproduct that gets generated, which has absolutely no use to that particular process or cannot be processed further, and something that needs to be discarded over the period of time, is called as a waste, right? So based on this, what do you say, the source, the waste can be classified into three different types. So can anybody tell me what are those three different types of waste based on the source, or you can say based on the nature of the waste? Yes, anyone? The physical state of this waste material, yeah. Yes.
Waste at the source, municipal, industrial, and agro
Yeah,
waste.
that is actually comes under the solid waste. So yeah, that is correct. So that is something that no, something related to the physical nature of the material. Yeah. So you have the solid waste, liquid waste, and the gaseous waste. So these are something that is based on the nature of the material. So yeah, we do also have the classification of the waste based on hazardous and non-hazardous. So that is the primary classification, and based on the physical properties, we have this or the physical nature, we have solid, liquid, and the gaseous waste. So how do you say that if I, let's say for example, before moving on towards the further classification in the solid waste, if I give you a particular solid waste, let's say anything for that example, like let's say I give you a particular sugarcane buggies or any kind of buggies for that matter or any solid waste, how do you determine or how do you tell me or what are the properties that the solid waste should have to basically confirm that this particular waste material is good for energy generation purpose? Yeah, you can say heating value. One is the it should have a high heating value, and then moisture content. Well, if moisture content actually degrades the, what do you say, quality or the property of the solid waste, it makes it not useful for the heat energy generation purpose. Yeah. So apart from that, yeah, you can say chemical elements specifically. Yeah, that is one. Apart from that, we have another one. It is the chemical constant, but I'm wanting what are that two elements that contributes to this calorific value. We have multiple carbon and yeah. So yeah, hydrogen. So you have multiple elements that is present in the waste material. So that's you can see in this, I guess, yeah, ultimate analysis we will be discussing. So you have something like carbon, hydrogen, oxygen, nitrogen, and sulfur. So among all these elements, the solid waste that have high carbon and high hydrogen content will be a better municipal waste. So this nitrogen, if you ask me a question on what about the other elements like oxygen, sulfur, or nitrogen, well, yes, the sulfur does adds up to the heating value or the calorific value, but nitrogen and oxygen do not add up to the calorific value. So the primary reason why nitrogen does not add to the calorific value is because that nitrogen, what you see, is actually inert in nature. So since they are inert, they do not undergo any kind of combustion or they do not burn, so due to which they will not be able to contribute towards the energy, or they do not, or they cannot add up to the energy of a particular substance. Similarly, O, that is your oxygen, in case of majority of the solid waste, they will be present in the form of moisture. As such, now just a few seconds before, as I said, the moisture content usually degrades the quality of your waste. So they basically prevent your material from burning, and they suppress the heating value or the calorific value of your system. So next comes is the, so similarly for liquid waste also we have certain characteristics makes it as a which makes it better for energy generation. So can anybody tell me what is it for the liquid waste? Yes. So for solid waste it was high carbon content, high hydrogen content, and a higher heating value. For what about for liquid waste? Yeah, BOD and TOC. Yeah, it is BOD, COD, and TOC. So I hope Obviously we will be discussing about what is exactly BOD, COD, TOC later in today's class or probably in the upcoming classes. But what is the full form for BOD, COD and TOC? Yeah, yes, yeah. So this is just no, total organic. Yeah, yeah, yeah. So this is just to make sure that I specifically ask this because sometimes we do not try to have an understanding on these what do you say, the full form. So we know what is BOD, COD and TOC, but we do not actually sometimes we do not know what does that term represent. So for that purpose I ask. And what about for gaseous waste? Excuse, I mean, can you just come, like, what do you say? Oh, yeah, I'm asking you what are the quality parameters for a gaseous waste that makes it suitable for energy production? Like, for solid waste, we talked about high heating value, and for liquid waste, it was BOD, COD. So, what about for gaseous state, gaseous waste? So, for gaseous waste, it is specifically your hydrocarbons and other fuel molecules. So yeah, so that is what makes them more suitable for energy generation or the energy production, or like makes this waste material suitable for energy generation. So going towards the solid waste content, so we have something like the classification of the solid waste. So I hope you will be able to recollect. So first one was the based on source. Next one is based on biodegradability. Excuse me, just a second. Just a second. Yeah, sorry for the disturbance. So as I was saying, so yeah, this solid waste are classified based on their source, based on the biodegradability, and based on the usability also. So as such, someone told based on the source, this solid waste are classified as municipal waste, industrial waste, and agro-based waste. Based on biodegradability, you have biodegradable waste, non-biodegradable waste. So can you just name a few of like sort of like examples for biodegradable and non-biodegradable waste? Y- Yes. And the non-biodegradable? Yeah. So plastics are the best example for a non-biodegradable waste, which is something that is happening today. So if you see, so the reason why the plastic as such, it takes a longer time. So usually their lifespan extends between 1000 to 100 to 1000 years. So they are one of the major non-biodegradable waste that is getting accumulated within the environment. And I hope if you go through any of the news articles, you can see so much concern regarding about the plastic contamination within the human body itself. So the microplastics, so they are contaminating the entire environment, and since they are so tiny, we which makes it where next to impossible to see through our naked eyes, so that is creating a major issue. So that is one of the example of non biodegradable waste. And based on usability, you have your organic waste, inert and recyclable waste also. So So now after this we will actually move towards the physical properties of the waste. So we have discussed about the solid waste. So liquid waste also has similar types of classification which is discussed in the course. Let's now move to the physical properties of the waste. So as such, when I say physical properties, what kind of properties comes to your mind which is related or not related to this waste matter? Yes, density. Yeah. Conductivity, okay. Let me just write it down here. Density, then particle size, and then, okay, okay. You can leave it conductivity for the time being. Apart from that, do you have any other physical properties? I mean, so since this course is porosity, yes, moisture content. So yeah, these are something that is very much related to your, I mean, the waste matter that we are going to discuss right now. So you have density, then you have particle size. Apart from that, you have conductivity, but it is not just normal conductivity or electrical conductivity. It is called hydraulic conductivity. And then you have porosity and moisture content, right? So yeah, so the porosity, moisture content, hydraulic conductivity, particle size, and density. So, what is the definition of density? So, it is nothing but mass per unit volume, or you can also call it a specific weight. So, can anybody tell me why density is also called a specific weight? Like, yes, density is fine, we all know it's a term, mass per unit volume, but why it is also called a specific weight? So the thing is, anything. Okay, so I'm leaving it to you to really think about why, because this word specific you can get it at many places. So please check it around, and you can let me know in the next class also. So in density, you have three different types of density that is related to this waste matter itself. So can anybody tell me what are the three different types of density? Yes, yes. And what else? Yeah, bulk density. Hmm. So this envelope density, it can also be termed as what do you say, apparent density. Yeah. So your bulk density basically includes both the pores as well as that of the voids, right? Sorry, pores as well as that of the interparticle spaces. Am I right or am I wrong? Yeah. What about for the first one? That's your absolute density. Only pore volume. Yes. No. Sorry. That is for envelope density or apparent density. What I'm asking for absolute density. So does it include or does it exclude? Exclude. So please be careful with these three definition. As such, I'm saying for everyone because there are chances that we also have a question in today's session itself where we will be discussing based on the definition. We will be having a multi-choice question to choose. Then we have something called as the particle size distribution or particle size. So based on the particle size, the processing conditions will change. So majority of this waste matter that you have or the processing of the waste matter is typically done in chemical reactors or any sort of a reactor. So these reactors basically work depending upon the size of the particle. So if the particle size changes, then we need to change the reactor as well as that of the processing condition. So that is one of the important reason why particle size is also an important parameter related to this waste material. So when you come to this particle size, uh, how do you basically measure this particle size, or how do you basically, like, among hundreds of particles, if I ask you to create a distribution, how do you go about analyzing this particle size? Yeah, sieve analysis is one. Then actually, based on the particle sizes, the instrument, or you can say the apparatus to measure this particle size distribution will vary. One is the sieve analysis. Yes, that's absolutely right. Then trommel, and then yeah. So so can you tell me why do we use like, based on what is the basis for this classification? I mean, that is the particle size. So which particular instrument is suitable for what particle size? Like for example, if you, yes, yeah, that is the basis. So that is the basis of the classification. So what I am more asking is, what is that particular size for which this particular instrument will be used? Like for example, if you say particle size analyzer, that is used for very small fine particles. So like that, why do we so for which type of particles we use the trommel? Yeah, yeah, and yeah, yeah, so that is correct. So based on these instrument, we do the particle size distribution so that we can understand what is the, so the reason why do we do particle size distribution is because each and every particles will be of different size, right? When you take a mixture or when you take a waste material, they will not be homogeneous in shape and size throughout their space. So they will be having some sort of a heterogeneity related to their sizes. So if you have something like a particle size distribution, you can really identify what is the major size of the particle, or what is the size of the particle that is predominant in the sample space that I'm considering. And based on that, we will be able to choose our reactor or choose our processing systems. So that is the reason why this particle size is important. Then we come to hydraulic conductivity. So what is exactly the definition or the meaning of hydraulic conductivity? Of course, conductivity is is something that it can conduct. It favors that particular process. But what do you mean by hydraulic conductivity? and why it is important here in our waste management systems. So Mm, moisture content, well, you can say that way, but the accurate definition is the ability of the porous media, or the ability of the pores that is present in the waste material to conduct water is called hydraulic conductivity. And specifically, the reason why this hydraulic conductivity is important in this particular in this waste treatment is because what happens is through this we will be able to understand how the water moves through the landfill. So for example, let's say you have a particular waste material, so there will be this water. Let's say for example a landfill is there, and that land and the water is, or let's say rain is pouring down, or it is, let's say it's raining, so due to which there will be the water, so the rainwater will try to seep through the landfill and then move towards the ground, right? Or towards the groundwater. So to determine how does this water move through this landfill to the underground, so that kind of a study is basically called as hydraulic conductivity. So by knowing this hydraulic conductivity, we will be able to have a picture on how does this water actually penetrate or percolate through the landfills that is occupying on the surface of the earth. Then apart from that, you have porosity as well as the moisture content. So porosity is nothing but the abundance of pores that is present in the material. Like if you have a particular volume of the material, how much amount of the volume is going to be occupied by pores. That is what is called porosity. And moisture content, again, I hope everybody will be knowing, it is the percentage of the water molecules that is present in the material. So if you have a certain material, how much amount of the weight of the material is occupied by the moisture is its moisture content. So this is about the physical properties. So the understanding of the physical properties is required so that we know what kind of process we can use to convert our waste to energy. So if you see, this waste to energy conversion happens through multiple processes. So it's not just one process. I hope you can recollect what was taught in the course. So one way of converting this waste to energy is through thermal routes, right? And then there are also other alternative routes for converting this waste to energy. So okay, so that will be, I think it will be covered in the subsequent lectures in the course. So based on this physical properties, we actually determine, or it basically serves as one of the criterias to determine whether that particular waste material that we are having can be converted to energy or not. So this is about the physical properties. Now moving towards the chemical properties, again in the we have two kind of analysis. One is the proximate analysis and another one is the ultimate analysis. So this particular pie chart basically represents the contribution from each of the material, or the percentage of the material present in that particular waste. So this is the pie chart, and this is for a particular biomass waste material, which depicts the percentage of ash, percentage of moisture, fixed carbon, volatile carbon. And then you have in the ultimate analysis carbon percentage, oxygen percentage, hydrogen percentage, sulfur, nitrogen, moisture, and mineral matters. So how do you do this proximate analysis? So there is a way, so there is a distinguished bit, so the way of how do you analyze this percentage ash, moisture, fixed carbon, and volatile matters, and then the way how do you analyze this carbon, oxygen, hydrogen, sulfur is different. So in case of proximate analysis, what you do is you take the waste material and then you burn the material, but that happens in the absence of oxygen. So please be careful. So whether the oxygen is present or not present is a huge factor in determining the constituents or the composition of the waste. If you are going to burn your waste material in the absence of oxygen, then you will be able to calculate the percentage of ash, moisture, volatile matter and fixed carbon. If you do it in the presence of oxygen, then you will be able to calculate the percentage of carbon, hydrogen, nitrogen, oxygen and other constituents. So specifically, the ultimate analysis is usually carried out. Nowadays, we have an instrument to carry out this ultimate analysis, and that is called as a CHNS analyzer. So C represents the carbon, H represents the hydrogen content, N represents the nitrogen, and S represents the sulfur content in the waste material. So we do have some questions related to how do you get to know the values of this particular elements. So that we will be seeing in today's lecture. So if you see in this proximate analysis, so you have moisture content and you have volatile matter, fixed carbon and ash. So ash is something is what you obtain at the end of the process. So you heat a material, you burn the material, and at the end, whatever the residue that you get is actually called as an ash. So how do you get to know the difference between moisture, volatile matter, fixed carbon, and ash percentage? Like, let's say if I give you a material, what kind of process you will do? Of course, I said it is burning without the presence of oxygen. So, if you do that, you will be able to get the moisture, volatile matter, fixed carbon and ash. So usually this moisture will get removed initially. So if you see through the lecture, the what it is stated that if you heat the waste material up to 105 degrees Celsius, all the moisture will be removed. Then upon prolonged heating, you will be able to remove the volatile matter. So volatile matters are nothing but those materials, or you can say that particular matter which will get vaporized as you increase the temperature to a particular extent. Once you heat upon that, or more than that, the material will start getting oxidized, and then the carbon that is present in the material will react with oxygen and form CO2. So based on the amount of CO2 that gets liberated, you will be able to identify the fixed carbon percentage that is present in the material. Apart from that, what is left is nothing but is called as an ash. So so now since I have told the process, can you tell me what will be the constituent in that ash, or what material is that ashes? You can say this residue. So what? Yes. Yeah, so it will be predominantly metallic oxides, or the metal impurities that will be present in the waste material. So this is about the proximate analysis. So yes, so since we discussed about the ash, and we, as someone rightly said, ash is nothing but it is the percentage of the impure metals or the metallic oxides present in the material. What do you mean by the fusing point of ash? Or what is actually the definition of fusing point of ash? So let's discuss this and then we will go to the ultimate analysis. What is the fusing point of ash, or what is the definition of fusing point of ash? Yeah. So the ash particles at a particular temperature, they will fuse, or you can say they can agglomerate or agglutinate to form a kind of a, you can say, a clinker like substance. So what temperature does this occur? There is a particular temperature range at which this ash fusing occurs. Well, yeah, that is correct, but it's partially correct because it's very broad, saying greater than 700 degrees Celsius. There's a particular temperature range. Yeah, 1100 to 1200 degrees Celsius. So this is the particular temperature range at which the fusing point of ash will occur. So seven greater than 700 is partially correct because majority of the fixed carbon will get liberated out as will get liberated out, but the ash percentage, when you say, it is typically something that comes more than 800 or 900 degrees Celsius. So that is the reason this fusing of ash happens at 110 to 100 and sorry 1100 to 1100 to 1200 degrees Celsius. So the question is, what I mean, ash is fine, we know that some material that is a residue, but why do we talk about a concept of fusing point of ash? I mean, why is there is a specific you know need to define a term like something called as fusing point of ash? Like as we discussed previously, hydraulic conductivity, there is a specific reason because we need to understand how the water is going to seep through the landfill to the underground. We need to understand that particular parameter or the that pattern. So like that, what is the need for understanding this fusing point of ash? Block the pores of furnace. Okay. Okay. So, well, we have an answer, but I'm going to leave this to as a question for today's class. We will be surely discussing this in the next class, but I want every one of you, every one of the attendees, as well as the participants who are not present in today's meeting, to think about the significance of this fusing point of ash. So let me write this: physical significance. Or does it even have any kind of a physical significance of as such? So I want every one of us, or like every one of you as well as the other attendees, other what do you say, registry, the people who have registered for this course, to think about, is there any physical significance for this fusing point of ash or the fused ash? So now we will move to this ultimate analysis. So here we, as such, we are repeatedly saying we find percentage of carbon, oxygen, hydrogen, sulfur, nitrogen and moisture. How do we determine this carbon, hydrogen, nitrogen, oxygen and sulfur? Yes, of course, CHNS analyzer will give us the results of what is the percentage, but how does that process occur in the system? Or what we do or how we treat the waste material to get the particular, you know. Yes. Yes. Hmm. Okay. Yeah, yeah, yeah. Yes, that's correct. And the nitrogen is using Jalda's method. Yeah. Sulfur? Yes. Yeah. Hmm. So, yes, that is absolutely correct. So, in case of carbon, you can use a combustion chamber where you can take carbon, react it with oxygen and form carbon dioxide, and then pass that through KOH to form K2CO3, and based on that values you can calculate the percentage of carbon. For nitrogen you can use the Jaldal method, and for sulfur you can treat it with barium chloride, that will form barium sulfate, if I'm not, I hope I'm right, and based on that we can calculate the percentage of sulfur. So if you know this percentage of carbon, sulfur and nitrogen, then you will be able to calculate the percentage of oxygen. Now, so moving on, we will move towards something related to getting the heating values in the system. I hope everybody is able to, like, what do you say, understand what I am discussing here. In case if you have any, what do you say, doubt, or if you are unable to, um, like, if you are unable to understand, then please you can unmute yourself and then let us discuss. Anyone? Anyone has any doubts? Shall I progress further? Okay. So we come towards something called as, so previously we discussed about heating value. So we discussed that having high C and H component content in your in your waste material, in your solid waste material, will be able to give a high heating value, and using that, and high heating value is good for a waste material to be used for energy production. So how do you determine this heating value? That is happens through bomb calorimeter. So this is the what do you say, the experimental setup for a bomb calorimeter. So this is the same picture as what you would have seen in the course, that it is adapted from there. So what happens exactly in a bomb calorimeter? So you have your material or the waste that is going to be combusted. That particular waste material is kept inside a bomb and then is locked. Excess of the oxygen, pure oxygen, is pressurized within the system. Once that is done, the entire system is placed or is submerged in a water bucket which with a known volume of water. After this, the bomb is ignited. So due to this ignition process, what happens is the waste material starts burning, and this burning of the waste material generates heat. So the heat generated by the bomb is actually taken up by the water surrounding that bomb, and due to which the temperature of that water increases. The increase in the temperature is usually detected by a thermocouple, which detects the temperature, and that temperature difference is recorded in a what do you say, the measurement equipment or system. So so based on this temperature change, we usually quantify heat, because as such we cannot measure heat, how much heat that is getting generated, we cannot measure that heat. We use temperature, and based on that temperature increase or decrease, we see how much heat is basically gained by the body or lost by the body. So this is something important. We cannot measure heat as such. We usually use temperature as a means to detect how much heat is gained in or lost by the body. So that's what becomes the principle of the bomb calorimeter. So this is extremely very important. The heat released during the combustion of the waste is equal to the heat gained by the bomb as well as that of the water. So let me just highlight this, because this is very important. The principle of the bomb calorimeter: the heat that is going to be released during the combustion of the waste material is equal to the heat that is going to be gained by the bomb and the water. So the heat that is going to be released during the combustion, we can represent it as delta H. So delta H is nothing but the enthalpy. Enthalpy is the heat that is released during the combustion, that is equal to heat gained by the bomb and the water, that is expressed as mass of the bomb Cp delta T plus MW delta T. So here we take, so delta T is nothing but the temperature difference. So initially, what was the temperature of the bomb? After that combustion process, to what temperature it has increased. So that difference is nothing but is the delta T. So let me just write this. Delta T is the temperature difference. So this combination of of the mass of the bomb CPB plus MW is nothing but it is denoted by a term capital W, which is nothing but it is called as the water equivalent. So this is the expression. So based on this, we will be what do you say, solving some of the question. I guess from next slide we have only questions. Yes. So any doubts related to this particular slide or any confusions you have, you are welcome to ask me. So we usually represent delta T as Tf minus Ta. Tf is the final temperature and the Ta you can call as the initial temperature or the ambient temperature. That depends upon the question that we are going to solve. It's better to call it as initial temperature. So, shall we move forward for today's questions? Yeah, okay. So, this is the place where, sorry, where you can answer to me. I hope everybody will be able to answer these questions. And in case if you have any doubts, confusion, please unmute yourself and then let me know what problem you're facing. So the first question for today and for this course is, which among the following density include both pores as well as the interparticle spaces in the system? You have bulk density, true density, apparent density, and envelope density. So I like to get responses from your side. Yes. Yeah. So bulk density is the one which basically includes both your both what do you say, both the pores as well as the interparticles spaces present in the system. Then what is this apparent density? Again, apparent and envelope density both are same, so I hope you'll be able to now answer that apparent as well as that of the envelope density is nothing but the density which include pores but not the interparticle spaces in the system. This will be absolute, I'm sorry. So bulk density is the density that includes both the pores and interparticle spaces in the system. Absolute density is nothing but it excludes both the pores as well as the interparticle spaces in the system. Apparent and envelope density both are alternative terms, but what it means is the density that includes the pores present in the material but excludes the interparticle spaces in the system. So let me just write this: excludes both pores and interparticle spaces. And this both is includes pores but excludes interparticle spaces. Includes pores but excludes interparticle spaces. So please have a good what do you say, understanding of each of these terms, because this will be something that may come up in your, I mean, that these are the questions that may can come for, you can expect towards your, the final exams that that some of you may take. The second question is, measurement of the density can be done by which of the following instruments? Pyrometer, pycnometer, anemometer, anemometer. Yes. Yeah. So measurement of the density is usually done by the pycnometer. So this pycnometer basically has two types of configuration. One is the tapping configuration and the other one is the, what is the other type of configuration? One is the tapping density arrangement, and there is another thing called true density arrangement. So this pycnometer basically works based on the Archimedes principle. I hope everybody will be having a good this thing of what is Archimedes principle is. So if pycnometer represents for the measurement of density, what is this anemometer or the pyrometer represents? Or it is basically used for measuring which physical quantity? Yes, pyrometer is for temperature, anemometer is for velocity, but it is specifically for to measure the speed of the wind. Yeah. So these if you see in this meteorological stations, you will have this anemometer which is used to find the direction as well as that of the specifically for the wind velocity. So let us write that pycnometer is for density measurement. So it's just a small suggestion from my side. Whenever you have some questions related to this objective multiple choices, it's always better to have what do you say, an idea of what are the other options mean, so that it is beneficiary for all of us to know what it could actually represent. I mean, what are those terms corresponding to? So next question what we have is hydraulic conductivity of MSW depends on its dash. So what is MSW? Anyone? Yeah, municipal solid waste. And this comes under what kind of classification? Anyone? Yeah, source. Classification of solid waste is source class. So what it depends on? Does it depends upon the particle size, fabric, both A and B, or none of this? Yes, particle size. Just give me a second. You can actually refer to the table because there are multiple factors which this hydraulic conductivity depends upon. So how many of you actually remember this? What are the multiple factors on which this particle hydraulic conductivity depends upon? It's a table. If you remember in the course, there is a table. So I'll be writing here. Please refer to the table. Of course, it's one of them is particle size. That is correct. But what about fabric? Does it belongs to this hydraulic conductivity or not? So let me leave this question for the time being. Please refer to the table so that you can also know you can have this thing on other what do you say, parameters that is responsible for this, or the other parameters that this hydraulic conductivity depends upon, because this is so these are the kind of questions you can actually be expecting in your assignments, or even you may expect during the final exams that some of you might take. So please refer to the table, and I will be marking this question. Let's discuss this in the next class. So now onwards, we will be having more of this, what do you say, numerical type questions. So let's start with something simple. So calculate, the first one is nothing but the weight fraction of the moisture content in the biomass sample. Consider the weight of the biomass before moisture removal to be 9.23 grams and the weight of the moisture biomass after the moisture removal is 6.565 grams. You need to calculate. So what is the answer? So it's a very simple question. The first subdivision. You just need to tell me what is the weight fraction of the moisture content in the biomass sample. You have the weight of the biomass before moisture removal and after moisture removal. Yes, any answers? 23%. I do not have an answer, so I also need to check. Let me just calculate. 20, how many percentage did you say? 23. Can you just check your calculation once again? 'Of course, I'm asking this weight fraction of the moisture content based on the dry weight of the material. So please keep that in mind while, what do you say, expressing your answer. Based on, wait, let me just write, based on the dry weight. Right. 28 point. So you have taken the denominator over there as 9.23 grams, right? So here I am asking based on dry weight basis. So you need to keep the denominator as the weight of the biomass after moisture removal. So I'll just write the formula. I will just write the formula here. So weight of sample. So this will be your formula. So next question is, consider a biomass sample. Again, the waste over here we are considering is 6.24 gram. Now this biomass sample is going to be heated to remove the moisture. Assume 25 weight percentage of the sample is lost as moisture upon drying the biomass sample. The bone dry is burned to 1000 degrees Celsius to derive the energy. The ash is recovered after burning and its weight is 2.53 grams. Calculate the percentage of the ash based on the moisture free sample. Let's come to this at the end. Let's move. So this I'm going to come back later. Let's go to the some other problems that is related to this course. Of course, these are something very similar to how do you calculate percentage of ash, percentage of moisture content. So I have given the formula for calculating the percentage of the moisture content for the first question. Let's move to the next problem before coming to this fourth question, second part. So here, so the question is, develop an equation for the combustion of ethane with first part is theoretical air and second part is 40 percentage of excess air, and determine the amount of air required for each gram of ethane burnt. Sorry, ethane burnt. So you have this particular equation. This is the skeletal equation that I have given. CXHY plus NO2 gives XCO2 plus H2O. Here you are supposed to develop a equation, a stoichiometric equation, where it is about burning off or combustion of ethane with the theoretical air is the first part, and you're going to use 40 percentage of excess of air. So for these two conditions you need to write an equation and then determine the air required for every 1 gram of ethane you're going to burn. So any ideas on how to go about this question? Because those two questions, these two are very simple questions, so you can have some, you will be having some idea on how to solve this. What about this question? Any idea? So let us solve this question step by step, because this might be a very new type of question for some of you. So what is the formula for ethane? Ethane is C2H, yeah, H6. So this is the ethane. And what will be the molecular weight of this? So it is nothing but 2 times, yeah, it is 30, but let me just write it. 2 times 12 plus, sorry, plus 6 times 1, that will be 30 units is gram per mole. So now this is for what is ethane. Now we have to develop a combustion equation, and over there the first part is theoretical air. So theoretical air is nothing but the stoichiometric quantity. But here the equation that I've given you, the skeletal equation, this skeletal equation has a mistake. Can anybody figure out and tell me what is that mistake that I have done in writing this equation? I have missed out on one particular element. So the clue is the word air. So I'm saying here CXHY plus N moles of O2 gives X moles of CO2 plus Y moles of H2O. So here I'm only using oxygen as the, what do you say, uh, here I'm only burning it in oxygen, but in the question I have mentioned it as theoretical air. So does air only has oxygen, or does it have also other constituents? Yes, I mean, air is made up of oxygen and also other gases, right? It's not just only oxygen gas that is present, that makes up air. Yeah, nitrogen. So that is what is missing here. I have not added nitrogen gas. Even though as I said, the nitrogen is inert, but still that will be, you need to consider that in this equation, because we are saying we are burning it in air. So that particular term also has to be incorporated. So we need to rewrite this equation. So that will be nothing but, let me rewrite it. CXHY. So I am writing the skeletal equation plus N moles of O2 plus, so this will be N moles of O2 plus N2, or your nitrogen, which gives X moles of your, sorry, X moles of your carbon dioxide plus Y moles of H2O. So this is the kind of a very bare skeletal equation for combustion of any hydrocarbon in air. But again, this is also incomplete because I have taken here N2, the stoichiometric coefficient for nitrogen, as 1, which is not true. So air, so what is the composition of air? Air has approximately 79 percentage of nitrogen, right? And 21 percentage of oxygen. So here I am neglecting the contributions from the other gases because even though they are present in a very minimal, what do you say, percentages. So predominantly we consider only nitrogen and oxygen is present in the air, and nitrogen makes up 79 percentage and oxygen makes up for 21 percentage. So if you consider this, then it means that for every one mole of oxygen in the air, you have 79 by 21 moles of nitrogen. Am I right or wrong? Yes. Is it fine, or is it like any what do you say, confusion, or anything that you are unable to understand? So for every so in air you have, out of the 100 percentage of the air, for that 100 percentage, 79 percentage goes to nitrogen and 21 percentage goes to oxygen. And as I said previously, I'm not going to consider the contribution from the other gases because they are present only in a very small percentage. So predominantly we are considering that the air is composed of only nitrogen and oxygen. And I am saying that for every 1 mole of O2, how many moles of nitrogen is going to be present? So that is nothing but 79 by 21, which is nothing but 79 divided by 21, 3.76. Are you okay, comfortable with this, or do you want me to? Is it fine? Again, here, this equation, you will have that, whatever that, so here, let me, so yeah, before that, is there any confusion related to this? How am I writing this 3.76 as the stoichiometric coefficient for N2? Anyone? Yes. If you have doubts, you're also welcome to please, what do you say? Write down, type down your doubt in the chat box. Anyone? So I hope nobody has any doubts, or if you have, please write it down in the chat box. I am progressing with this question right now. So this is 3.76 into. So since, as I said previously, nitrogen is inert, so it will not be going to participate in that combustion. So it will come out. It will be 3.76 in H2O. So this is the skeletal equation which you can use it for any hydrocarbon, not just ethane, propane, butane or methane, whatever. So this will be the skeletal equation for the combustion reaction of the hydrocarbon in air. So now we have to modify this equation for ethane that is there in this question. So that would be nothing but C2H6 plus, and let us balance the reaction, plus 3.76 x. This I have made a mistake into, plus 3.76 and 2. So now we need to balance, and we need to know what is the value of what do you say, n here, xy. So since I hope you will be able to balance, so can I get to know the values of x, y and n? X and y you can easily get. So if you can get x and y easily, n is very easy. So x value is, so 2 carbon on the left hand side, so 2 carbon will be on the right hand side. So can I say x value is 2 and y value is 3? Balancing of chemical equations. Is it fine? X value as 2 and y value as 3. Okay. So if x value is 2 and y value is 3, then what is the value of n? Yeah. No, you have, yeah, okay. You have n, it is O2, right? So 2n will be equal to 7. No, no. Why do you say that 2n cannot be equal to 7? No, n can be even 3.5. Yeah, because stoichiometric coefficient need not be always a whole number. It can also be a fraction. It cannot be a negative number or 0, because having a 0 means that particular component is not there. But it can always be a fraction, or it can also be a whole number. So n value is 3.5. C2H6 plus 3.5 times 2CO2 plus 3H2O plus this value will be exactly the same. So you just need to multiply what is 3.76 times 3.5, 13.16. So this is the equation. So please check whether everything is getting balanced, all the atoms on the right hand side, on the left hand side and right hand side. You have two carbon, two carbon. I hope my pointer is visible. You have two carbon on the right hand side, left hand side, two on the right hand side, head 6. So here also you have 3 times 2, that is 6 hydrogen atoms. Then you have totally on the right hand side 2 times 2, 4, 4 plus 3 is 7 oxygen atoms. And on the left hand side 3.5 times 2, that is again 7 atoms of oxygen. And nitrogen is again 3.76 times 35, that is 13.16 nitrogen atom, yeah, nitrogen molecules on both these sides. So this is the equation. If you are going to exactly use theoretical percentage, so this 3.5 times 3.5 times of O2 plus 3.76 times N2. So this parameter or this quantity is going to be your theoretical air percentage. Now for this we need to calculate. So for this we need to now do the calculation. So they are asking us determine the air required for each gram of ethane that is going to be burnt. So here what it is mentioned is 1 mole of C2H6 requires 3.5 moles of, am I correct? I hope, is this what it actually this equation means, that for 1 mole of the C2H6 to burn you require 3.5 moles of air. So now the question is, for 1 gram of C2H6, let's say XY is Z, okay, Z grams of air is required. we are supposed to calculate what is the value of Z. So what will be the value of Z? It's just you need to do cross multiplication. So I have given 1 mole of C2H6 is nothing but 30 grams. So let me write that here. 30 grams of C2H6 will be requiring 3.5 times O2, that is 16. Oh sorry, that is 32 plus 3.76 times 28. Okay, there is a query. So I'll just so just be, in the just be on the line. I will take up this question at the end of the lecture. So we have 15 more minutes left with us. So just be on the line. I will discuss. I mean, I'll tell you how to, watch these lectures. So this will be nothing but 3.5 times 32 plus 105.28. What is this value? 137.28 times 3.5. 480.48. Now you are just required. So for 30 grams of C2H6 or the ethane that you burn, you are going to require 480.48 grams of air. So for 1 gram of C2H6, how much grams of air are you going to, or how many grams of air is required for burning? What is the value of Z here? Let me bring this up. What is the Z value? Yeah. So what is that value? 480.48. Yes. 16.016 gram. Please, it's my suggestion again. Whenever you say some, what do you say, a physical quantity, please do mention the units behind that. So grams of air. So Z value is 16.016 and that represents 16.016 grams of air per gram of ethane. To be very clear, of air is required for 1 gram of ethane, or for burning uh, is required for the combustion of 1 gram of ethane. So this is the basically based on what is the theoretical air that is required. Now you need, there is a part B also for this, which states that if I'm going to use 40 percentage excess, and then how will my equation change, and what will be the quantity of the air that is required. So again, it is very simple, I think, since now you know. Just a second. So it's just that from this theoretical air percentage, you are just going to have 40 percentage more. So this is the theoretical air requirement. Let me just write that. This indicates your theoretical air requirement. So 40 percentage more of this is what you are supposed to use for the next question. So I hope you will be able to solve this. But again, any question that we are unable to solve due to time constraint, we will be taking up in the next class, so you need not worry about that. But I would actually like for you guys to take that as a home task or a home assignment, and then try solving it and coming up with some answers so that we can discuss in the next class. So I'm going to leave this question here for the 40 percentage. I'm going to leave it to you guys. You please uh, write it down, and then or take it down in your notebook or wherever you are taking, or wherever you're solving this question right now, and then let's discuss that particular part in the next class. So before all these questions, yeah, let's go to question number 7 before we finish for today. A solid waste is having 1% sulfur is combusted in a bomb calorimeter. The temperature of the bucket water, that is where you're going to place your bomb, is increasing from the temperature of 25 degrees Celsius to 30 degrees Celsius. Water equivalent is given, that is nothing but your W value, which is 2402 calorie per degree Celsius. 1.5 gram of sample is used for the test, and the wire is par 45C10 wire is used for ignition. It is observed that 3.4 centimeter of the 10 centimeter, the total length of that wire is 10. 3.4 centimeter is going to we remain unused. So that is not going to be used up. It's going to remain unused. Now to titrate the calorimeter, we are going to wash it with 24.2 ml sodium carbonate of 0.0709 normality. N, it's not M, it's not molality, it is normality is required. Calculate the gross heating value of the waste in joule per gram. Consider that the thermometers are working perfectly. So how do you go about solving this? This is exactly very related to the course, or what we have seen in the week 1 lecture. Hmm. Yes. Hmm. Okay. So yeah, that is exactly what is required. So I would like to ask one more question before solving. Can I take the, I have mentioned here that the weight of the sample is 1.5 grams. Can I take more than this? Can I take, let's say, 5 grams of sample and then do my analysis? Are you sure? Okay. So if you read the bomb calorimeter section of our lecture, or yeah, so over there it is clearly mentioned that the weight of the sample that you're going to take should be between 1 to 1.5 grams. So please be I mean, it is not a big this thing, but it is better to be aware of how much sample we need to use, because all these bomb calorimeter that's fine, that's completely fine. These kind of instruments, they will not be requiring that much amount of sample to do the analysis. So we are determining the percentage of the carbon, hydrogen, nitrogen and sulfur and all the other stuffs, heating values and stuff, but then the amount of sample that we are going to load here in all these instruments is very little. So it's something that we need to appreciate, because we have very less sample and we can do many analysis that we actually want to do, or that will be useful for us. So minus E2 minus E3, the entire thing. The T over here represents for delta T, so that divided by M. So can everyone solve and let me know what is the gross heating value? So what is the delta T? Water equivalent you have, so that is given in the question. So 2402 times delta T. Yes. Okay. E1. Yeah. Sorry, that is C1. E1 is nothing but the molarity of Na2. Sorry, normality of Na2CO3. Okay. E2 is, what is the value of E2? Yeah. So that into percentage. Hmm. Hmm. Yeah. Okay. 6.6. Okay. What is now E1? Yeah, that is true. Weight divided by the weight of sample is 1.5 grams. Now I want to know what is the value of E1. So it is 24.2. Okay. Hmm. Okay. So what is the final value, Hg? I am also calculating in my personal calculator here. So it is 2402 times 5. 12010. Okay, 12010 minus 13.7, 20.55. Yeah, 15.18. So by 1.5. So what will be the answer? Yes, answers. So shall I? So it is 120. Okay, let me just check once. 11950.7 by 1.5. 7966.71. What is the unit? Calorie. Okay. So the question here I have asked is to calculate the gross heating value in joule per gram. So we need to convert this into joules. How much is one calorie is how many joules? - 4.184. Okay. 7966.71 times. So the answer multiplied by 4.184. 33,332.72 joule per gram. 33,000, sorry, 333, 332.72 joule per gram. This can also be expressed as 33.332 kilojoules per gram. So this is the gross heating value, or you can also call it as JHV. I know I'm just mentioning the short form, JHV. So you also have something called as HHV and LHV, which is nothing but high heating value and low heating value. So those concepts are there in the lecture. So we do have one more question, but we are actually running short of time right now. So let's mark question 6, question number 8, and question number 4, the second part, for next class. So do you guys have any doubts related to what we have discussed today? So related to the query that came, so they were unable to attend the class from the starting. So this session is actually getting recorded, so you will be receiving the recording very soon for this week. So by Tuesday or Wednesday, you will be able to see this recording in the YouTube, as well as the presentation will be made available to you. So I'll also say how to access this presentation. So you do have that course homepage, right? So for this waste to energy conversion, that course homepage, if you, on the left hand side, if you drop down, you will be finding a particular section called as problem solving session January 25. So if you click that link, you will be directed to a Google sheet where you can find the link to this where you can find a link to a YouTube video. So that YouTube video will is nothing but this session that is getting recorded now, as well as you will also find the link for the presentations which I'll be uploading. So I'll modify the presentation a little bit so that it is, you everybody can understand, so that the participants who are not there in the meeting today also can understand that. So I hope that answers the question. So if you have any queries, please let me know now, or if you have any feedback that you also want to give regarding the way I am taking or the pace at which I am taking, or do you want anything or any kind of a suggestion for me to improve, so you're welcome to do so now. I'll stop presenting. So is there anyone who has any doubts or any kind of a feedback that you would like to share before we conclude our session for today? Otherwise, we can conclude our session. Uh, yes, are you? Mr. Rakesh, are you like, do you want to say something? Because I'm unable to hear you. Oh, okay, okay, okay. So if nobody has anything to say, then I think we can conclude our session for today. So thank you everyone. Okay, there was a person. Uh, so I have received a, what do you say, a query that the person is unable to understand the last problem. I guess if I'm not spelling it wrong, I guess Spartan. So can you please be specific on what you are unable to understand in the last problem? Is it that the entire problem, or is there anything specific? Okay, so let me describe it very quickly. So here what we are supposed to calculate is, yeah. So we are supposed to calculate the gross heating value. So you can check the definition in the course. So the gross heating value is calculated. So this is based on the bomb calorimeter principle that we discussed here. So here you see the principle states that the heat released during the combustion is equal to heat gained by the bomb and the water, and that is given as delta H is equal to W times delta T. So this delta H can be represented as mass of the material that you are going to burn times the gross heating value, right? So you're going to just equate this M times Hg is equal to the water equivalent times delta T. So here that E1, E2, E3 that you're seeing are nothing but the correction factors that usually come up in the systems, because the entire heat that is going to be released by the combustion will not be taken up by the water. Some amount of the heat will get expended, in this what do you say, that in that fuse wire, and some amount of the energy will basically go with the titrating the calorimeter, and the some amount of the energy will actually go up with the sulfuric acid, that sulfur that is going to get combusted. The solid waste is having that 1% sulfur. So sorry, it's not sulfuric acid. So that E2 actually represent for the amount of energy that is going to get combusted, that is going to get utilized in combusting this 1% sulfur. So this E1, E2, E3 are nothing but the correction factors. So let me take up that equation for you here. So it is M times Hg is equal to W times T. So T here represents for the delta T. So delta T is nothing but the temperature increase in the water because of the burning of the waste material in the bomb calorimeter. So if you just bring that Hg, then it will be W, that is your water equivalent, times delta T by M. And as I said, since that entire energy is not going to be utilized by your, what do you say, by the water, whatever the energy that is getting released by burning the waste material is not going to be exactly, or the entire energy is not going to be exactly taken up by the water. So you have these correction factors. E1, that basically comes from this what do you say, calorimetric, this washing, minus E2, which comes from the combustion of the sulfur in the waste material, minus E3. E3 comes from this fuse wire. So some amount of the fuse wire is also going to be get burnt, right? So that will also take up some amount of the energy. So these three will, these three should be included here. So this will be the gross heating value, and there are formulas for calculating the E1, E2 and E3. So E1 is nothing but it is the volume of sodium carbonate. Like that, E3 is calculated by 2.3 times the length of the wire used up, and E2 is nothing but 13.7 times percentage of sulfur times your mass of the sample. So this is how you are going to calculate. I hope it is fine now. If you have any, do you have any other questions, or do you have any questions related to this? Yeah, so if you have any questions, then I I will ask you. For the time being, you go to the course. So this will be the fourth lecture, characterization of waste, uh, 2 it will be. So that is the course. So you go to that course lecture, you will be able to understand, or I will take up from here in the next class. I hope that is, yeah. So or otherwise we can take it from the next class. So let me just conclude the session. Oh wait, I am sorry. I think I didn't share the screen, right? Oh, sorry. Okay, I didn't share the screen. Okay. So I'm sorry. Please see this recording so you'll be able to understand. Yeah. So let's just conclude our session for today. So thank you everyone for joining today's session. Our next live interaction session will be on 2nd February from 5 p.m. to 7 p.m. Sunday. So till then, please keep working on your assignment, and we will meet next week. Thank you and bye.